G'day chemistry students. In this video we're going to be looking at dot point 2.3.1. It's our first introduction into concentration concepts. Let's get stuck into it. So first off, I guess if we're talking about concentration, the word that you probably are attaching to most or maybe linking to quickest is the term concentrated. We're also looking at then its opposite, or inherently looking at its opposite, diluted. And this is a spectrum of concentration that we look at. If something is concentrated or diluted, it belongs on a spectrum of concentration. And what we're looking at is the amount of stuff that can fit inside another, which is a very broad way of talking about concentration. But let's say I have a liquid and I can dissolve or put stuff, other kinds of particles into it. I can then also measure its concentration, again, the amount of stuff that's in something else. We can also have concentrations for gases as well, but primarily in this topic, we will be looking at the concentrations of liquids. Notably as well, when we talk about things that are diluted and concentrated, for colored substances or colored solutions that may be dilute or concentrated, we usually associate the darkness or depth of the color or the saturation of the color even to sort of determine how concentrated something might be or how dilute something might be. Now, there are two ways to form concentrated and dilute solutions. One is by having the same volume. This is a factor that, or a variable that can affect concentration, but having the same volume here and changing the amount of solute that's being dissolved. So if we dissolve more solute into a liquid, then what we'll find is that the substance is considered to be more concentrated. Whereas if we're only going to dissolve a little bit of solute into a solvent, then we would find that solution is dilute. The other factor that I just talked about a second ago is volume. So here what we would have are two different beakers with solvent in it. They would have the same amount of solute, the same amount of salt. But what this is demonstrating here is if we only put in a little bit of the solvent, say water, we'd end up with a higher concentration of solution. Whereas if I had the same amount of stuff that's dissolving, the solute, and add more solvent or maybe water in this case, we would end up having a lower concentration of those solute particles. Now note when we look at these two particle diagrams, what we can see is that the red particles are the solute, the things that are being dissolved, and the white particles are the water or whatever solvent is doing the dissolving. So a higher concentration means that there are more of the solute particles in a space surrounded by the solvent. And that space is a particular measured volume. Now, there are lots and lots and lots of different ways to measure concentration. In particular, and this is the one that we will focus on by far the most in this course, is molarity. If we can count the number of particles, or specifically the number of moles of solute that we put into a liter of solution, we can measure the molarity. So that is big M, or measured in moles per liter. Now, the other one that we may look at from time to time, or you might even begin to be asked to convert between, is mass per volume. So not the number of moles or the number of particles, but the mass of the substance in a certain volume, usually expressed in grams per liter. Now, as chemists, usually we like to talk about moles per liter because it enables us to talk about different solutions when they are reacting with each other. And this is very important most of the time when we're talking about chemistry in theory. However, when we're talking about chemistry in practice, let's say in an industrial setting, we're mixing different solutions together, trying to make new chemicals. On the ground, it makes the most sense for people to be making solutions given instructions that are in grams per liter. So then all the person would have to do is measure out the number of grams that they are required to make however many liters of solution. Then this happens a lot in some laboratory, but especially so in industrial conditions. Now, the other ones don't come up all that much. Some of them are based on percentages, so maybe a mass percentage or a volume percentage are some noteworthy expressions of concentration that we can also use. And these parts per one, they're really, really good for comparing concentrations for trace elements of or trace molecules or substances with extremely low concentrations. But for now, I just want to sort of introduce them as they are, and we might look at them in context in further topics when we need to. Now, in a second, I'm going to be moving over to a simulation. In this simulation, we're going to be playing around with some of these concentration concepts. What I'm going to be showing you is that one factor is the amount of substance that you add that has an impact on concentration, and the other is volume. Let's get over there. Okay. So before we get started, what I want to do is sort of orienteer ourselves and show you what some of the elements of this simulation can do. So first off, I can pull this tap and fill my container up with water. I can also use the tap down the bottom to empty my container. I can shake my container of solid up here to add solid to the mixture and form a solution. And there is a solution button as well. I'm not really going to be playing with that one. It doesn't do too much for us. I'm just going to be working with solid. And we also have this probe here, which can measure the concentration of the substance. Usually I put this in the bottom corner. If we empty things, it'll still give us a reading, because if it's off in the open air, it won't give us a reading. So I like to put it in the corner there. What we can also do is evaporate the solution as well. Anyway, let's go, and you can remove the solute too and just get pure water back. Anyway, I'm going to reset this. I'm going to be working with copper sulfate today. So what I have first is half a liter of solution. There's no copper sulfate in there, so its concentration is 0 moles per liter. What I'm going to do is add some solute. And what I can see is that the concentration of the substance is now at 0.510 moles per liter. Now, what that means is if I had a liter of the substance, there would be exactly 15.10 moles of substance. Because I have half a liter, what that means is I have about 0.255 moles of copper sulfate in my half liter of liquid. Now what you'll notice is that if I add water, I'm going to dilute my solution. So the solution went paler or less saturated in color. And my concentration was halved because I doubled the amount of water that I had inside. Notice that I can also evaporate my solution. And what I'm doing is removing the water without removing any of the copper sulfate. So what I have here again is an increased concentration once I've removed my water. And then I can again fill it back up with water and decrease my concentration again. Again, evaporation, increasing the concentration, dilution or addition of water, decreasing it again. Now note that if I just remove the water, the concentration doesn't change. There's still the same amount of substance in a set volume in the liquid that's here. All I'm doing is just pouring it out. That will reduce the number of moles of copper sulfate that are present in the container. There aren't as many as what I started with before. Note that when I dilute it again, I kept reducing my concentration because there aren't as many copper sulfate particles in there anymore. I got rid of a lot of them at the beginning. So again, I can keep removing liquid, diluting again, and that reduces the number of copper sulfate particles. Now, if I add lots and lots and lots of solid, just give it a sec, lots more, a little bit more, a little bit more. What we'll start to see is that the copper sulfate is now saturated. It's so concentrated that it can't hold any more copper sulfate particles. So anything that I add settles to the bottom, it doesn't dissolve, and you'll notice that the concentration at this point will not change. All I'm doing is adding more solid. So the concentration that's being measured here is just for the copper sulfate in solution that's dissolved in the liquid, not any of the solid that's sitting at the bottom. Now notice I can remove some of this liquid. This stuff is still sitting at the bottom saturated. All right. all of this solution is still saturated, the concentration hasn't changed. But as I dilute and add more water, there's more space for that solid to dissolve and enter into solution. And so what we end up having with now is not a saturated solution, but one that has a concentration lower than the point of saturation. Now, there are lots and lots and lots of different things that you can use this simulation for, and hopefully it will help you to start getting your head around some of those concentration concepts that we will continue to explore over the next few weeks. But yeah, let's conclude this lesson now. Thank you very much, everyone. In the next video, what we're going to be doing is looking at some concentration calculations. So when we're looking at these kind of calculations, we're looking at how to determine the concentration of a substance, or maybe vice versa, if we know the concentration of the substance, maybe trying to calculate something like the number of moles in the solution that are present. But until then, have a good one.